Professor Herzon. How are you?
Hey, good morning. You're always the first one on. How you? All right. Okay, so you don't need to copy this down. You already have it in your notes, but I would just want to put it up here for you. So we said that, the first step is going to be protonation of the alkene by the hydrochloric acid. And that hydrochloric acid generates a key intermediate, which is this carbocation. And we're basically going to spend the lecture talking more about carbocations. And so the other thing that I want to remind you of is the relative stability of carbocations. So they're sensitive to substituents, and their stabilities have been well measured. So, or carefully measured. And again, this is review, so you don't necessarily need to copy it down. Okay. So a carbocation with one carbon attached to the cationic center is a primary carbocation, 2 secondary, 3 tertiary. And the tertiaries are the most stable. So we can say that the relative energy is 0. And then the secondary is uphill by 16 kcals. And then the primary is uphill by 35. So tertiary most stable, primary least stable. And so they're very sensitive to what's around them. You get 15 kcals essentially when you change the substitution pattern. That's a big energy difference. Okay. The second point is that if you look at my energy diagram here, I drew the carbocation pretty high in energy. In fact, it's close to the transition states, right? And, we've talked about, not overinterpreting the accuracy of where I've placed things on these diagrams, but it's generally true that the carbocations are going to be very high energy species, okay? And what you might notice from this transformation is that, or from the energy diagram, is that if you consider, put the reaction aside for a second and consider this hypothetical scenario. So I had a carbocation sitting in solution, this one in the middle, and I was going to either react it by elimination of a proton to generate 1 butene, or addition of chloride to make the 2-chlorobutane. So think about the carbocation as your starting material for a second. The activation energy to get away from that carbocation in either direction is pretty low, right? And when I say the activation energy specifically, I'm talking about that, right? And so this is because the carbocation is just so high in energy. And so the point I'm trying to make is that when you have high energy reactive intermediates, it is very easy for them to funnel down different reaction pathways, because you don't have to put a lot of energy into the system. You're already there. You're already, it's like you've already, you've revved your engine, you've got the parking brake on, and you're ready to pop the parking brake and take off. So one of the very interesting things that carbocations will do, because they're so high energy, is that they're going to do what we call a rearrangement, okay? And these are very cool, often unexpected. We're always sort of got our ears to the ground thinking about them when we're trying to figure out structures in the lab. It's best illustrated with a simple example. So I'm going to take this molecule, which is tert-butyl ethylene. Okay. And we'll treat it with HCl. So same reaction we did with our old friend 1-butene. And if you're following the content closely, hopefully you can draw at least the expected product, which would be the product of chloride bonding to the more substituted position. And I'm just going to drop stereochemistry because it's not important. Okay. So this is what we would expect. I hope you would expect it too, based on what we've discussed. We expect you to expect it on Friday. So this turns out to be the minor product, okay? That is not, in fact, the major product from the reaction. The major product is as follows. Okay, and so the question is, how did we make that? What's going on here? All right, unexpected. Okay. If it helps, we can label carbons. So if I call these A, B, and C, here we've got A, B, C, A, B, C. Okay, so the proton ends up where we would expect it. The issue is the chloride in the product. We expect it to bond to carbon B, but instead it's bonded to carbon A. And the methyl group has moved. So if you look, there's 3 methyl substituents on A in the beginning. Now there's 2, and there's 1 attached to B. So what it's done is, the punchline is it's a carbocation rearrangement. Okay, and the mechanism. So the mechanism involves first protonation of the alkene. So bring in the HCl. Okay, so first we're going to protonate, get to the expected intermediate. And then instead of chloride trapping, we're going to invoke a carbocation rearrangement and a specific rearrangement known as a 1-2 shift. And so the methyl group, and you can pick any one, is going to migrate over to the secondary position. And when it migrates, it takes its electrons with it. So okay. And so what you end up with, then you have to be careful about electron counting, but you're going to move that positive charge over to the A position. So and so let me just A, B, C, A, B, C, A, B, C. Okay. So, so the methyl group has jumped. And again, this may strike you as unusual, and it should, because we don't just move bonds around molecules. We wish we could, but because the carbocation is so high in energy, okay, there is not a significant barrier to this process. And if we ignore the specifics of the molecule and just consider the relative stability of these two cations, this is a secondary cation. This is a tertiary cation. And so when I do that migration, the system's going downhill by about 16 kcals per mole. So it's very favorable for it to do this, okay? The corollary to that is that that doesn't happen in the other direction, at least not synthetically. So there are enzymatic systems that can kind of overcome these, sort of the parent rules of thermodynamics. But for our purposes, you don't run these types of migrations in the other direction. So you don't go from tertiary to secondary, because that is going from a more stable to a less stable cation. Okay. And so if that gets trapped by chloride, let me go black here. If that gets trapped by chloride, then you get to the major product. The one that we're calling unexpected, okay? And so where does the minor product come from? The minor product comes from a little bit, of trapping of this secondary cation. So if this gets trapped by chloride, okay, you can get some of that minor product, okay, and that is indeed what happens. It's not 100 and 0. It's 90 10 or 80 20 in that regime. You may be wondering, why? Like, why does this, why doesn't chloride just trap it before it can rearrange? I hope you're wondering that, because it's an important point, which is that the rearrangement of the carbocation is what we call a unimolecular process. So there's only one molecule involved. And if you consider, what sort of what has to happen there, that carbocation doesn't need to find anything else. It's all sort of there already. If you consider the chloride trapping to form the minor product, that's what we call a bimolecular process. So there's two molecules that need to come together, in this case, an atom and a molecule. And so for that to happen, they need to find each other in solution. And so there's going to be a concentration dependence there. There's going to be a temperature dependence. And so these types of bimolecular processes are generally slower than a unimolecular process. And so the rearrangement can occur. The other thing, as I said now, is helping speed this up is just the reactivity of that secondary cation. It's so full of energy, just wants to lose energy, and so it's very easy for it to do this shift. All right. So, so what exactly does this look like in terms of orbitals and transition states? And so let me go to another board here. All right. I can put this on an energy diagram. And so let me redraw. And I'm just going to drop that hydrogen I was showing in green because we're not really thinking about that anymore. Okay, so there's my secondary cation intermediate. And we know that the tertiary is going to be, it's going to be down here. And so it's going to look like this. Okay. And then there is, despite the high energy of the cation, there's going to be a barrier, but it's going to be very small. Okay. And that barrier corresponds to the transition state. Okay. The top of that saddle corresponds to the transition state for the rearrangement. The difference in energies here is equal to, hopefully you can guess it, 16 kcals per mole. Okay. And so we want to know what's going on from a molecular orbital standpoint in the starting material, in the product, and then what does that transition state look like? Okay. And so I'm going to start by drawing out the starting material. In this case, the secondary cation. That cation, that carbon center has three things. And so it's trigonal planar. And there's an empty 2p orbital perpendicular to the plane of that defined by those atoms. Okay. And then we need to draw in the adjacent substituents. And so I'm going to show stereochemistry here. Okay. And the question is, what's interacting, right? How does that methyl actually move? And what's interacting is the carbon-carbon sigma bond that holds that methyl in place. So if I draw that bond, it's going to look something like that. And I can shade it any way I want. So I'll shade it such that it overlaps correctly with the 2p orbital. Okay. And it is going to migrate via a transition state, which I'm not going to draw right away, to form the other cation. So let's just redraw the more stable tertiary cation on the right. Okay. And so the methyl group has moved over. And so it's going to be pointing up. The existing methyl group is down. Hydrogen in the back. And then my new cationic center now has gone planar. So it's rehybridized, gone sp2 hybridized. I've got an empty 2p orbital. And so it looks identical to what I started with, except now I've got two methyl substituents attached. And this then is the new sigma bond. So sigma CC, sigma CC, okay? And so now we can think about the transition state. And remember Hammond's postulate, transition state looks most like the thing closest in energy to it, be it starting material, product, be it an actual bona fide intermediate, okay? In this case, it's an intermediate. It's the secondary carbocation. It's much closer in energy to the transition state than the tertiary. And so if I'm going to draw this, I'm going to draw it so the transition state looks a little bit more like the secondary cation than the tertiary. And so we can do something like this. Okay. And so that methyl group with its lone pair, or not its lone pair, with its pair of electrons in the sigma bond is like walking over to the adjacent p orbital, okay? If we consider the number of electrons sort of under discussion here, it's 2. You have 2 electrons in the sigma bond. The p orbital, of course, is empty. And so we call this a 3-center, 2-electron transition state. Okay. And so it proceeds through this transition state. And the transition state, because the secondary cation is higher in energy, it looks a bit more like the secondary cation. You know, we'll never ask you to kind of, you know, we're not going to split hairs on this, but it looks more like the secondary cation. So you've got, you know, approximately still tetrahedral geometry. At the carbon bearing the migrating group. This thing is near planar. It's, you know, it's not perfectly planar anymore, but you get the idea. You're starting to make those geometrical changes to get to the new cation. And so it's in fact those changes in geometry that create this little barrier. And so if you consider what's happening with the adjacent methyl substituents, the one on the left is planarizing, okay? So like those methyls are coming up. So if you imagine they're sort of down with my hand, they're coming up, right? And then the methyl and the hydrogen at the right-hand carbon, that carbon is becoming tetrahedral, so those are getting pushed down. So what's happening is basically I'm pushing those methyl groups and that methyl and hydrogen in the back past each other. Okay, and so there is in fact an eclipsing interaction, right? We've seen this. Hopefully you can connect this back to just the butane ethane conformers. There's an eclipsing interaction between the substituents, and that is where the barrier comes from. And, you know, we can guesstimate it. We know we're about 3.3 for the methyl-methyl, and we're about 1.3 for the methyl hydrogen. So you're approximately 4.6 kcals. And that's probably, you know, we calculate it to get a more accurate number, but that's probably pretty close to what the actual barrier is. That's where most of the input needs to, you know, that's what most of the requirement is for energy. So anyway, so these things are super interesting. They've been around, you know, people started studying carbocations in the 40s, and there was actually a very famous feud in the literature. Let's take a quick digression here between Saul Weinstein and H.C. Brown. So both of these guys were Nobel laureates, and there was a very famous cation in organic chemistry known as the Nor-Bornyl cation. And so this molecule on the left is norbornene. It's a strange name. If you take this and protonate it with acid, you can protonate the alkene. So don't let the structure of the molecule confuse you, this is identical to what we did with 1-butene and HCl. But then these things start to rearrange. And so you get a CC shift to go over there. And so you form a new cation. Okay. And there's a transition state for this 1-2 shift that I'm not going to draw orbitals, but maybe I'll just draw it sort of as partial bonds. So okay. So you've got this system where you are essentially in the transition state having bonding to both carbons, okay? And I just told you that, you always want to rearrange to go to a more stable cation. So here we're going secondary to secondary. What's happening? If you actually redraw this bottom cation, you'll see that it's identical to what we started with. So they're what we call degenerate cations. And we don't mean that in a derogatory sense. And so anyway, Weinstein and Brown got into this very colorful argument over the nature of this rearrangement. And Weinstein, I believe, was arguing that you have these two carbocations in equilibrium with each other, proceeding via this transition state. And Brown was arguing that it goes through this transition. Brown was arguing that the transition state is in fact the cation. So if you imagine the barrier for that rearrangement getting smaller and smaller and smaller to the point where it's actually equal in energy, now it's, you are the transition state. So it gets in, it's a very hard question to answer. And it gets into, sort of almost, philosophical issues of what, constitutes an intermediate, what constitutes a transition state. But there's a lot of very interesting chemistry associated with this system. So anyway, for our purposes, we'll assume that we're not going to get into any heated debates over what's happening. We're going to agree that we're forming a cation. It proceeds, if it does rearrange, it will proceed through a 3-center 2-electron transition state and rearrange to form the more stable cation when it can. Okay. So you need to constantly be on the lookout for these things, right? And, they are very common, and they're common enough that when you get rearrangements, that's often diagnostic of mechanisms. So if you get a product and it's got some weird rearranged skeleton, first guess is usually going to be, okay, we're probably making a carbocation somewhere, because that's going to be typically the way these things happen. So, okay, so how are we doing on time here? All right, we're good. So yeah, so carbon's not the only thing that can migrate. Hydrogen can migrate. So
Professor,
yeah,
I have a question. So when you're talking about the 3-centered 2-electron transition state, what are the 3 centers that correspond to that?
yeah. So the 3 centers that kind of refers to are the center bearing the positive charge, the atom that's migrating, in this case carbon, and the atom that's attached to the migrating atom.
Thank you.
Yeah, so 3 atoms, and then we're ignoring the rest of the molecule. And then if you just think about how many electrons, ignoring the rest of the molecule, how many electrons are involved? There's 2 electrons. So it's 3 center, 2 electron transition state. Okay, good question. So all right, so carbon's not the only thing that can migrate. Hydrogen can migrate, and in fact, if you're given an option typically hydrogen will migrate faster. So, whoops, what happened there? Sorry. Okay. Okay, so when you're given an option, typically H is going to go there. It's not a hard and fast rule, but it's a good guideline. And so, for example, if I take take our substrate that we were using before, and let's just convert one of those methyl groups to a hydrogen to get to something like that. Okay. Treat that with HCl. So similar or identical reaction. Bang. Oh, let me go red there. Bang, bang. Okay. You get to you get to this type of secondary cation. So the only difference here is that we've removed one of the methyl groups that was on the on this alkene substituent. Okay. And so it's a secondary cation. If I migrate, I can migrate either a methyl group or a hydrogen. Okay. And if I migrate a hydrogen, let me show you what happens. So if we go this way, so H migration. Okay, I get to that cation. If I migrate a methyl group, if we migrate a methyl group, you end up with this. So okay. And so so we start with the secondary cation, and H migration gets me to a tertiary cation. Methyl migration gets me to a secondary cation. Okay. And so can the methyl migration occur? Yeah, because I'm on this kind of this very high energy system. These two secondary cations are probably almost identical in energy. But there's a better option, which is to migrate the hydrogen, because then I go down to a tertiary cation, pick up 16 kcals per mole of stabilization. The system is much happier. And so that is kind of the basis for this generalization that typically hydrogen's going to migrate. And just the way it works out is that, if you move the hydrogen and keep the substituent where it is, you end up with a more substituted cation than if you migrated the substituent. Okay. There's also an orbital effect to it, which is worth mentioning. So because H donates a 1s orbital to the sigma bond with carbon, that 1s orbital, of course, is not directional, it's spherical. And so it has better orbital overlap. The resulting bonding MO has better orbital overlap with the adjacent 2p orbital. It's less sort of localized between the H and C than a carbon-carbon sigma bond is localized between a C and C. So there's a shape effect that also makes the hydrogen migration more facile. Okay.
Professor Herzon, if the rearrangement to get the secondary carbocation occurred, would it be possible then for like a second rearrangement to occur to get it like then to the tertiary one, or that just like wouldn't happen, if that makes sense?
No, it could happen. Yeah, for
Okay.
sure. Yeah. And so it's going to depend, it's a great question. So this is where you get into this idea of unimolecular versus bimolecular. So it will depend how much it's going to rearrange is going to depend upon how fast chloride can get in there and kind of put an end to it. You know what I'm saying?
Okay, so in like a low chloride environment, it'd be more likely that the secondary carbocation would eventually rearrange to a tertiary carbocation. But in a high chloride environment, if a secondary carbocation occurred, it would likely then just create the chloride product then.
Yeah, exactly.
Okay.
Exactly. It would get trapped. And, and where, what defines high chloride, low chloride is going to depend on the system, how hindered the molecule is, and stuff. But the trend is exactly right. So the rearrangements are unimolecular. They have a certain rate associated with them at a given temperature. And then, you've got a rate of trapping with chloride that, has all sorts of dependence on experimental parameters. So, yeah. And you do see that, I could show you guys, maybe I'll put it up next time. There's a very famous molecule known as pleromidolin that we've worked on in my group. It's an antibiotic, but nature makes this thing. It's beautiful. It's basically this cascade rearrangement process where you get 4 or 5, things migrating through one cation. And so, this guy recently identified all the enzymes that make this, and it's 6 enzymes that put this molecule together, which is beautiful. So, all right. So are there any questions on that material? Because right now we're going to shift gears and I'm going to introduce acid catalyzed hydration of alkenes. So if there's anything that you'd like clarified, I'd like to do that, about carbocations, because they're going to come up again and again and again here. So let's take a minute and open it up to questions. Ryan, yeah, go ahead.
On the energy diagram between the tertiary and secondary cation,
no, next one.
Yeah.
Or where did I draw it? Here it is. Yeah.
Yeah. It looks like there's like a new methyl group on that. So, like, where did the hydrogen substituent group go? Does that?
Did I mess something up here? So I think I have it correct. So in this one, so it's this, it's one of these methyl groups that's migrating over.
Right. I guess my question is, like from the original structure with like the double bond, or that carbon like bonds to a new hydrogen, I thought, from the HCl.
Oh, it does. Yeah. So, okay, let me just, I think I know what you're saying, but let me just check here for a second. Yeah. So you protonate at the end. Okay. And I condense that in this drawing into this CH3 group. Does that get at your question?
Yeah. Okay.
Yeah.
Thank you.
I just stopped drawing because it was, gets to be too much. Yeah.
I have a question about when you drew the transition state that I asked a previous question about. That's hyperconjugation, right?
Yes.
Okay.
This
So
is
do
what
we
I'm
need
trying to tell
like-
you guys. Okay. You just need to know hyperconjugation. And honestly, like I want to make a little handout like I did for MO, and unfortunately I won't get it to you before the first exam, but I'm gonna try and do it this weekend. If you know hyperconjugation, if you understand that orbital interaction, it's all the same. It's just perturbations on that interaction. So yes, so we are starting here with basically a hyperconjugative interaction between the CC sigma bond and the empty 2p orbital, okay? And that we just take that hyperconjugation interaction and just kind of let that, wiggle around, and all of a sudden you've got the transition state, and then you've rearranged. So yeah, it's great insight. It's all the same.
And then I also have another question about when we talk about like major and minor products, is it always going to be the case that or do we, so I guess my question is, do we have to know, or is it possible to know if there's going to be a major and a minor product for a specific reaction? Like, is it always going to favor like a configuration where the order of the carbon increases?
Yeah, so this kind of gets at what Caroline was asking about. So we're going to assume that if we generate a carbocation, that you can do that you're going to have time to do a rearrangement, okay? And so that will lead to, in practice, that will lead to a mixture of products, and the distribution, as I said, will depend on the experimental parameters, but there will be a major product. And so, in terms of, asking you questions about these types of things, we won't ask you to say, give us percents, but we'll say, identify the major product. And so, what that type of question gets at is, do you see the rearrangements, and then the trapping, to give you, which would give you the predominant product. Does that get at your question?
Yeah, thank you.
Okay.
I had a follow-up to that question. Just for the purposes of the exam on Friday, since it's up through lecture 9, should we just be expected to draw the minor products of these reactions, where chlorine, for example, would be bonded to the most substituted carbon?
Yeah, I mean, you can sort of put a firewall up with there's not going to be any carbocation rearrangements. We'll also, I will not give you any problems that there could be, so you don't have to like artificially exclude them. Like, yeah, basically don't worry about carbocations for Friday, or carbocation rearrangements. You need to worry about carbocations because those were in lecture 9, but the rearrangement stuff that we're talking about, don't worry about it. Yeah. All right, I'm gonna keep going just because we got 5 minutes. If you have more questions, please just stick around after class. But we're going to introduce acid catalyzed hydration of alkenes, and this is sort of an important, point in the course. And so, we've talked sort of, we've tried to cover, we have covered a lot of ground very quickly up until this point, talking about VSEPR, MO theory, carbocations, alkene geometry, hopefully a lot of that was review for you. Hopefully you've seen at least some of it in Gen Chem, and for those of you that may have had some exposure to organic chemistry. Now we're going to move to a different type of sort of knowledge or content, which is we're going to start talking about reactions. And these reactions, and maybe I'll just say these comments and then we'll just end because there's no point in just cramming this in here. These reactions may at first seem to be unrelated, okay? And many of them are. So you'll just have to like learn them separately, but many of them are quite similar, okay? And for example, the first reaction we're going to talk about will be acid catalyzed hydration of alkenes, okay? And the mechanism of that transformation is strictly analogous to the addition of HCl to an alkene. We're just changing the reactants a little bit, but the same issues, you're going to protonate, carbocation, look out for the rearrangement, trap with the X minus. In this case, it's going to be X. In this case, it's going to be water. Okay. And so, I think this is, it's very, in terms of your studying and stuff, you really want to try to bring it together into as unified of an intellectual framework as possible. So you really want to, group things both in your notes and in your mind, bin them by mechanism. Okay, so, if I have, and we'll limit, we'll keep it to what we've discussed so far. So if I have HX plus an alkene, right? And X can be water, X can be chloride, bromide, iodide, okay? What's gonna happen, right? And what HCl will do and all of it, all the sort of, vagaries of that process. And so the same is going to apply for every single reaction that proceeds through the same mechanism. So the point I'm trying to make is, like, as much as you can focus on mechanism, you don't need to memorize every single little detail. It's great if you do, like, that's great. But what's more important is getting the mechanism. So as we work through stuff, try to see the homology between what we're discussing. It's the same thing that just happened with the hyperconjugation. It's there's connections between all this material. And if you can get the mechanism down cold, then you're in a situation, on an exam or whatever, or you're in lab. Suppose you go and work in an organic chemistry lab, you're confronted with a new reactant. It's perplexing. But you look at it and you say, okay, well, that's a strong acid, for example, and I got an alkene. I know what happens. So let me just start there, So try to really focus on, first and foremost, like unifying the content and organizing it around mechanism, and then backfill with, specific details, as much as you can. But that'll really help you in terms of keeping up and, not feeling overwhelmed, because we're going to be doing like a reaction or two a day, which, it's going to be a laundry list pretty soon. So hold on. All right. I'll stop there. We'll do acid catalyzed hydration after the exam. I will distribute, I hope, as soon as I hear back from Porvu about the proctors, I'll distribute instructions on that, hopefully today. And, I'll send out like a finalized, sheet of instructions for the exam. And then good luck. We'll see you on Friday. And I'll stick around here if anyone wants to chat.
Professor Herzon, I just had a quick question just generally about the exam. So we can only write on like paper. We can't like write on our iPads. Is that correct?
I don't know. So my original
Okay.
plan was for you to scan and upload, but apparently Canvas
Okay.
has something. So I need to talk to Porvu today. For now, assume it's going to be paper.
Okay.
But it may change. Yeah.
And secondly, no calculators, correct? Like all the math that we're asked to do.
No
like,
calculators. Yeah. Yeah.
Okay. So like we won't be able to like be asked to calculate like the ln of like
No.
112 or something. I don't know.
This is why we love organic, because there's
Okay.
very little math. Yeah. So,
Okay. I just wanted to make sure because
Yeah.
like I can
No.
barely add 1 + 1 some days. So
That's okay. Yeah. Yeah, no
Okay, thank you.
calculators. You can use models, but you should have the models with you. It's still a lot of people on the line. So, please don't ask us to like get up and go do something,
Mhm.
just want everyone in front of their screens for
Yeah. So we can have just like our modeling kit like next to our computer and stuff. And can we have like things like not like pre-built, but like, for example, like I have like this, like is like that fine? Or like does it need to
Yeah,
be
no,
disassembled before the
do it.
exam?
Yeah, that's great.
Okay.
Yeah, that's fine.
Okay.
Professor Herzog, so this may sound like a dumb question, but I know we didn't go over like all the addition reactions in like lecture,
Mhm.
but like I'm assuming like, are those still on the midterm? Do you know what I mean? Like, because all we did in class was like, or at least in lecture was like HX, but like I know there's like others that were in the book. So like, should we also keep those other reactions in mind, or should we mainly focus on like?
No, again, I mean, we can keep it to HCl, that's fine. Because again, what do you learn by, HI versus HBr versus HCl? You know what I'm saying? They're all the same reaction, just different components. So
Like
Yeah.
it's not like we won't need to know like halohydrin formation or like hydration acid catalyzed. And
no, that's coming. So we're a little out of order with the book, but that's sort of on the horizon here. So yeah, you don't need to know that.
So it's just addition of HX to form alkyl halides.
That's the only one that will be on the exam. Yeah.
Okay.
Yeah.
Cool. I wanted to make sure it wasn't like
Yeah, it's not a dumb question. I think we're out of sync with the book, which is why, and so obviously you're reading the book, which is great. So yeah, don't worry about the other stuff for now. Just the stuff I did in lecture.
Okay, thank you.
Also, sorry, like related to, we have to finish suppling chapter 4 then before midterm, or
So what does the whatever's due? I think it goes up through chapter 4, right?
yeah, right.
Yeah.
But I
yeah. So you guys
feel like chapter 4 is not total, but that's fine.
Okay. I can take a look, but yeah, I think that's what we've done in the past. But I'll double check it.
I was just going to ask another housekeeping question. If the week 3 answers for the like group problem set had been posted somewhere or emailed, or if those are forthcoming.
Sorry. Yeah, I'll get them up today. Someone asked me about that. Yeah.
Thank you.
I have a question.
Oh, sorry.
Okay. I have a question about kind of Juan Caroline's question. So like, even though we won't have calculators, will we be expected to like know certain formulas that we've gone over in class, like delta G formulas? I know those were in like the textbook.
I'm not, no, because you can't really, I mean, the delta G, the free energy, you should know that. Should just know that, period. But we're not going to ask you to do any math with it.
And then along this similar line, so like there are like tables in the textbook with like alkyl groups.
Mhm.
So, should we have those like memorized, or is that not part of what is expected for this exam?
By tables, you mean like naming them?
Right, yeah.
No, I mean, you should know what we've talked about in class, which is basically like methyl. We had ethyl on that I think week 2 problem set.
So not like the short branch chain, like isopropyl and stuff like that.
No, again, it's not that significant. I'd rather you guys focus on like the concepts,
And like with that, we don't need to know like, oh, that's a ketone, like that's an ether, that's an ester. Okay.
No. Again, as much as you can, short answer is you don't need to know that for the exam, but as much as you can start to pick that up, that's great. Because we will, well, actually I won't, but in the second semester, you're going to have a chapter on ketones and a chapter on ethers. And so, you'll get formally introduced to those functional groups. I think we actually might do ethers, but ketones are certainly second semester. But for now, just in discussing the chemistry, it's good to know them, but we're not going to ask you to identify, different functional groups. Yeah.
Thank you.
Yep.
I just wanted to clarify on something you said during lecture about H migration. You mentioned that H migration is usually preferred because first, in the example we went over, it forms a tertiary carbocation.
Yeah.
I just wanted to clarify like the second reasoning. You said because of the shape of hydrogen's orbital.
Yeah. So let me just draw it out. It's if you consider, sort of what a CC bond looks like. So if I have a CC bond, you know, the inputs are going to be we're going to assume these carbons are excuse me, are tetrahedral. So this is what type of orbital?
It would be an sp3 orbital.
Right. Yep. Okay. And then if we say that, all right, next to that, we're going to have a 2p orbital. Okay. So that's the orbital interaction that we're thinking about for a CC migration. If you go to a hydrogen instead, okay, the inputs are different. So we have an sp3 orbital and then an H1s orbital. Okay. And, you know, we can shade them. This should be up here, but you get the idea. And the point is that the H1s because it's spherical, okay, it's actually like pointing more towards the adjacent 2p orbital, you know, like the resulting MO, the bonding orbital resembles the H1s because that was, you know, part of the input. And because that H1s is spherical, the resulting orbital kind of has bigger girth. Okay, like this orbital is, you know, if we were to sort of look at the width of these bonding orbitals, this is, you know, going to be X and this is going to be Y. And, you know, Y is greater than X. And so it's just, there's less there's less bending and twisting that it needs to occur before you start to get overlap between the 2p orbital. Does that answer the question?
Yeah, that makes sense. Thank you so much.
Yeah.
Professor Hartong, when we were asked to draw the bonding shape for two sp2 or sp3 orbitals, do we like draw the two like little ones on the side or not? Because I feel like in some solutions there's just a sort of elapse or something.
Oh yeah, I think I know what you're saying. So like if I draw a sigma bond, draw it like this,
Yeah, right. Do I
or draw it like this one up here?
No, I think some solutions don't have those two like little circles on the side, just the center part.
Okay. Either way is fine. The important point is that you show a bonding interaction between the carbons for the bonding orbital, and an antibonding between the carbons for the antibonding orbital. That's like the most salient point. You know, that's like kind of the critical thing. The exact shape of the orbital, you know, we're not, you know, you really, again, you have to really calculate it to get an accurate answer. And, you know, the things that we're drawing, you know, it's really a vast oversimplification. Because, yeah, you know, if you go on to take it, you know, an advanced organic, if you take quantum, I think you'll probably get this. But, you know, there's no such thing as, you know, a localized CC sigma bond. That those electrons are actually spread over the whole molecule, and they're like mostly between the carbons. But like if you calculate the orbitals, you'll see orbital all over the place. So why do we do this? We do this because it, you know, it helps us to talk about it and think about reactivity. So all that is to say is, yeah, we're using a, you know, a crazy simplified version of what actually exists. And so we just want you to get the key point that, you know, bonding, same sign between the atoms, anti-bonding, change in sign. And then also I should add to that, you know, sigma has the symmetry about the bonding axis, pi has the node. Those are kind of the most critical things. And then, whether you put the little sort of tails on or not, is because either way is wrong, really. Is the answer. Yeah.
Great, thank you.
We'll
Totally
criticize.
makes sense.
Yeah.
I had one is more like a quick question. The other one's like a concept related question.
Mhm.
So, the first one is I just want to make sure I'm getting this right, so I don't like end up focusing or putting like, because I tend to like zoom into things a lot, so I don't zoom in the wrong stuff, and then I end up not knowing what
Okay.
I need to know. So the concepts focused on in lecture are the things that we should more likely be going over versus like, I mean, obviously the chapters as well, but like mainly like we should focus on the lectures is what I'm saying.
100%.
Okay.
Yeah. There's additional stuff in the book that we're just not covering.
Yeah, like those stuff. Like
Yeah. Don't worry about it, because
Okay.
it's too much. Like, it's too much. It's like you can't. We've this course has been sort of tuned as much as possible to kind of minimize the scope of the coverage while still giving you everything you need to know, and that still fills the semester. So there's a lot of stuff in the book. There's like stuff on petroleum, I think, or something, I can't remember, but there's a lot of like little one-offs that you don't need to worry about. Yeah, you could use the lecture notes as a filter and just have them side by side with the book, and just make a little notation of what was covered in the lecture, if that that might help you to sort of sort through it.
Okay,
Yeah.
got it. Thank
Yeah.
you.
Yeah.
And then also, I remember one concept that came up one term that came up on the PSET was or the sapling. Sorry, I call like everything PSET because we used to do that. But the like global versus local minimum, and I was wondering what the difference was.
Yep. So the term local, the term global refers to the whole system. So like when you're looking at those energy diagrams, the global minimum, I think this is a true statement. The global minimum is going to be the lowest energy spot on that diagram. Okay. The local minimum is going to be sort of focusing in on, say your two carbocations. So let me give you an example. Suppose I had like, some olefin, some alkene, some product. Okay. And then, it could rearrange. And let's say there were two cations up here. Okay. We would say the global minimum is here. If we were talking about the cations, we'd just be looking up here, and we'd say the local minimum is here. So the term local minimum, has to always come with a descriptor, like, the local minimum for the carbocation, or, the local minimum for the intermediate. So you know what we're talking about. But global, I think, is unambiguous. It's the lowest energy spot on the diagram.
Okay, so the global minimum is like the lowest energy spot versus local minimum is one of the lower ones, but like not the lowest one.
Yeah, exactly. So, what we would say is that, thinking about, in the context of like carbocation rearrangements, if you could rearrange a secondary cation to a tertiary cation, that would give you a local minimum in the on the reaction coordinate. So it's a way of saying, we're not going all the way to product or to the most stable thing on the reaction coordinate, but just considering this cationic intermediate, the tertiary is going to be the minimum.
Okay.
Yeah.
Thank you.
Any other questions? If not, I'm going to sign off because I have an exam to write.
I have a quick question on
Yeah.
today's lecture. So we were talking about how there could be either the methyl or hydrogen substitution for the carbocation or movement, and we prefer the hydrogen over the methyl.
Yeah.
So when we're thinking about major and minor products, does that methyl shift now become a minor product compared to the H? So like there's like two minor products.
Yep.
Okay.
Absolutely. And this is it's what makes it interesting, but also challenging to actually do experimentally, is because you can end up with, a bunch of different stuff in there and you need to sort it out. And that's not always straightforward.
Okay. Thank you so much.